homework so was page 214. Okay, so I gave you 2 to 10, was it? Yeah. Right, 2 is okay, 3 is okay, 4 is okay, 5 you want me to do? Yeah. Okay, so oh dear God. Right, number 5, A and B are two independent events, so they're telling me they're independent. So that means the probability of A intersection B equals the probability of A multiplied by the probability of B. I know that is true because they told me they were independent events. Okay, then it says if probability of A is 0.4 and the probability of A union B is, use the formula that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B, right? So we know that that's 0.4 and we know A union B is 0.7, right? Okay, if we just draw a Venn diagram. Okay, so if this is A, this is B, we know the two of them together are 0.7, yeah? Okay, and we know A, so the red circle is, we know that's 0.4, don't we? Right, okay, then we know this here is 0.3. Okay, so what will I do now? Probability of A, probability of A intersection B. A union B is the probability of A, which is 0.4, plus the probability of B, I don't know, minus the probability of the P of the intersection. Wait now. So, hang on now. Are two independent events? Yeah, I'm stuck on this 0.7. Can I come back to it there in a minute? I need a minute to think about that one. Okay, so I'll come back to it in 5 minutes. When I give you something to do, I'll come back and have a look at it and I'll get the answer and I'll come back to you. There's no point in me humming and hawing in front of you. Right, is number 6 okay? 7? 8? 9? 7 part 2? 8 part 2. 8 part 2. I hope I don't have to think about this one. Right, 8 part 2 reads, explain why A and B are independent. That bit? Is that the bit? Yeah. Yeah, so you do probability of A intersection B is equal to the probability of A multiplied by the probability of B, and that works out to be true, and that's your explanation.
Well,
so,
part 1 I got 1 over 15 and last one it says 2 over 15.
So part 1 is the probability of A intersection B. So they tell me the probability of A is 2/5. The probability of B is 1/6. So these two together are 3/5, is it? 2/5. Yeah, and these two together are 1/6. And the whole lot then would be 13 over 30. Is that what they tell me? Am I looking at the right sum? I am. So the whole lot together is 13 over 30. So add these. So add 2/5 and 1/6. So when you add 2/5 and 1/6, you'll get, that's 12 over 30 plus 5 over 30, 17 over 30. Is that correct? Right? So, but you're only allowed to have 13 over 30 in there. So when you add them together, you have an extra 4 over 30, don't you? So that has to go in the middle. So 4 over 30 will go in the middle. Is that okay? Ashley, do you see where that came from?
Yeah.
Right, okay. And then 2/5 take away 4 over 30. 2/5 is, what did I say, it was 12 over 30, take away, that's 8 over 30. Right, I know you can cancel it down, but who cares? This is 1/6. 1/6 is 5 over 30, so that's 1 over 30. Is that alright? Okay, and then it says, explain why they're independent. So the intersection is 430 over 30. Probability of A is 2/5 probability of B is 1/6. I must have done something wrong. Did I calculate something wrong? Because that's not equal.
Yeah, no, it's not.
I think that was two.
Yeah, that's 2/30. Have I done something wrong?
No, it's 2/15.
Oh, explain why they're not independent. I thought it was explain why they're independent, and I was getting the wrong answer. So 4/30 equals 2/30. That's why they're not independent, because they don't satisfy that. Is that right? Okay, right. That was number 8. Number 9.
Yeah, when you do it.
Yeah, number 9. Right, number 9 reads, the probability of C on condition D is equal to 2/3, and the probability of C intersection D is equal to 1/3, right? And they tell me they're independent, right? Okay, if they're independent, right, the probability of C on condition of D is not going to affect, right, C. So the condition 1 is actually equal to the probability of C. Okay, that's true for independent events, that C on condition of D is actually equal to C. If I said probability of D on condition of C, what would that be equal to? Probability of D. If I said the probability of A on condition of B, what would that be equal to? Probability of A, right? That's only true for independent events, okay? So, because one doesn't affect the other, so probability of C on condition of D doesn't affect it at all, so it's just the same as probability of C, right? So probability of C is 2/3, and once you have that, then you want the probability of D. So the probability of C intersection D is equal to the probability of C multiplied by the probability of D. So you know 1/3 is equal to 2/3 multiplied by the probability of D. So then probability of D is equal to 2/3 divided by 1/3, which is 2, which isn't right. What have I done wrong there now?
I think it's 1/3 divided by 2/3.
It's 1/3 divided, oh, I have it the wrong way around, sorry. That makes sense, and it'd be a half then. That makes sense. How did I know I was wrong there? Because I got probability more than 1, okay? So I got a probability of more than 1, so I knew I was wrong, okay? So, is that right? So probability of D is a half. Are we okay with that?
Yeah.
That was 9. Is 10 okay? 10 okay? Yeah. Right, okay. I might give you a few more of those to do in a few minutes. Right, okay, I'm going to move on to the next bit. Right, next section. And you're going to read through the last section yourselves, because the last section is just a load of crap, really. Right, okay, so you're going to do the last section yourselves, right, in a few minutes. Okay, right, so the next bit is probability involving permutations and combinations. So basically, there's nothing new here. It's just you have to use what you learned in permutations and combinations and apply it to probability. Okay? So there is absolutely nothing new here. So there's no new formulas or new methods or anything like that. Okay? It's just what we learned in the first 2 sections of probability 1, right, we have to use again here. Right? Okay. So we have, I'm just going to go straight to an example. Right, so example 1 is going to be question 1 on page 218. Okay, so question 1 on page 218 says, a hand of 4 cards dealt at random from a normal pack of 52. So you've 52 cards, and you pick 4, right? So you have 52 cards and you pick 4, right? Find the probability that the hand contains exactly 2 queens. So part 1, you want the probability that when you deal 4 cards that it will be exactly 2 queens. So,
You turn off the light on the...
do you know what, I need to turn off the second switch there. Will someone jump up and do it? Sorry. So the switch nearest me. Yeah, thanks. So the probability of 2 queens, right, that's the question. What's the probability that you would select 2 queens? Right, let's see how many cards you can pick. So if I just pick 4 random cards, I have 52 choose 4. I can pick it in that many ways, and when you put that into the calculator, it's 270,725. Okay, so that's how many ways this is how many ways you can pick 4 cards. Any 4 cards. So not necessarily queens, right? You can pick any 4 cards. Right, okay, so probability you can pick any 4 cards is that way. Right, now you work out how many ways can you pick 2 queens. So how many queens are there in a deck? How many queens? There's 4, and you want to pick any 2. So 4 choose 2, girls. 4 choose 2 is 6. Okay, so this is how many ways you can pick 2 queens.
Miss, why is it so close to the
Yeah, because you're picking 2 queens out of 4 queens. So then, what's the probability of selecting, when you deal 4 cards that you get 2 queens, you have 6 in 270 over 725. That's the probability of picking 2 queens. Is that alright?
Yeah.
Okay, does that cancel down? Probably, I don't know. Right, okay?
No.
Right, are we okay? Are we okay with that? So, we have to, the probability is your last step. You have to work out how many ways can you pick 4 cards, and then you have to work out how many ways can you pick 2 queens. Okay? Right, so part 2 of the same question, have I caught anyone off? I've moved it up. Right, part 2 of the same question says, what are your chances of picking 4 spades? So again, you're dealing 4 cards out of a deck of 52. So we know we have 2,725 ways of picking any 4 cards. We have to work out how many ways you have of picking 4 spades. So how many spades in a pack? Spades, how many spades? There's 13 of them, isn't there? And how many do you want to choose? 4. So 13 choose 4 works out to be 715. Okay, into the calculator, the answer is in front of me, that's how I know the answer. Just in case you think I'm working them out in my head, I'm not. Right? Okay, so that means there's 700, so your probability of picking 2 spades are 750, say that again? Yeah, sorry, 4 spades. Probability of 4 spades, right? 13 choose 4 is 715 over all the different ways you can choose 4 cards. So 270, 725. Okay, and does that one cancel down? It does. 11 over 4165. Remember, you don't have to cancel probability down. You can give them as the fraction doesn't have to be in its simplest form. Right, can I do over here part 3? So part 3 reads the probability of getting 4 red cards. So what are your chances of getting 4 red cards? So you know all the different ways you have of picking any 4 cards. So you just have to work out the probability of picking 4 red cards. How many red cards are there? There's 26 red cards, and you want to pick how many of them? 4, so it's 26, choose 4 into the calculator with that, and you'll get 14,950. So then what's your probability of 4 red cards is equal to 14,950 out of a total of 270,725.
That equals 46 over 833.
46 over
833.
833. Okay? Is that right? And then there's one last part. Okay? So, what's the probability that you pick 4 cards of the same suit? So that just means you want to pick out of any 13 cards, because that's how many is in the suit, you want to pick 4. So 13 choose 4 is, what's it? 715, sure we did it already, didn't we? 715, right, okay, but you can pick 4 spades, can't you? Or 4 hearts, or 4, what have I missed out, diamonds, or 4 clubs, isn't that right? So we know that's 714, because that's 715, because that's 13 choose 4. Or means you, which is 715. Or means you add, which is 715. And or means you add, and 4 clubs is 715. Is that okay? So how many different ways have you of choosing 4 of the same suit? You add all those. 2,860. So then the probability of choosing 4 cards of the same suit is equal to 2860 over 270,725. Is that okay?
Yeah.
Right. So we've used our combinations to work out the number of different ways before you put it over the probability. Is that right? And if you see the examples in the book, what they do is they work it out at the end. So they'll go 13 choose 4 plus, or means plus 13 choose 4, or 13 choose 4, or 13 choose 4 out of 52 choose 4. So if you look at the examples in the book, right, they tend not to work them out. I like to work them out as I go along, right, whatever you're into, right, whatever suits you. Is that alright? But if you look at the examples in the book, that's what they have there, right? Okay, will you do me a favour, will you, page, you don't have the page, I'll put number 2 up in Teams. Will you do number 2? Right? Yes. Say that again. Something about signs? You have a meeting with Miss Lyons and you have to go, right, friends? Okay, so I'll put up question 2 there in Teams. Will you have a go at question 2 for me now, and then we'll correct it?
On page 218.
Page 218, question 2, yeah. Okay, it's gone up there. No, it's not. It's not gone up yet. Now it's gone up. Yeah.
You said what day Christmas starts?
Yeah, not the first Tuesday back, the second Tuesday back, so it's I think it's the 10th of November, just give me a sec. Is it? It's Tuesday the 10th, so it's not the first week back, it's the second week back.
Do you know the revision class that week? We use that revision class, like you said, go over certain tests.
Yeah, I can. That reminds me, exam questions this week, I'll throw you out a few, but what topic will I pick? So will I pick algebra, probability or statistics, or will I do a mixture of all three? Do a mixture of all three? Right, okay. I'll have it for you tomorrow. Yeah, just question 2. Have you done?
No.
7.5 number 2. There are the answers there if you want to check them. Actually, you're coming to me at 12:15, yeah. And Leah, you're coming at 12. Do we get the right answers? Right, we're happy with number 2? Right, okay, I'm doing number 3, you're doing number 3 now, and then we're moving on. Right, as in, we're doing the last section, so we're finishing this chapter today. Right,
And are we just revising for the weekend?
yeah, we won't start anything new until after midterm. Yeah.
But are we doing this?
I'll have to think about that one. It's not fair. Yeah, and it's not fair that we'll be doing maths and then you'll be going out the door and going up and doing a French test and stuff like that. So, can you leave all those decisions with me? Don't ask me yet. Right, okay. So, number 3 is next, okay? Put up the answers. It's number 3 up there, so.
We're not taking notes from the next section now, we're just reading it.
No, we're just reading it because when you see it, there's nothing to take. It's pretty obvious, right? It's just a bit of theory and yeah, there's not a lot to it. Part 2 and part 3, right? Hang on now. Tell me the page because I'm after losing it. 216 or something, is it? Part 2 and part 3. All 4 discs are different in colour, so that's 1 blue, 1 green, 1 red, 1 yellow. 2 of the discs are blue. Is that one? What's it? Am I looking at the right one? The disc?
Yeah.
All 4 colours are different in colour, so that's a blue, a green, a red, a yellow, right? So to work out, if you pick one blue, one red, one yellow, one green, okay? Work out how much that is. And then for the last one, 2 of the discs are blue. So out of 5, you want to choose 2. And out of the rest of them, which is 3, 9, 11, out of 11, you want to choose 2. Last one, 55 over 182. Yeah. You got it? Yeah, yeah. What part are you on? Part 2. The 4 discs are the same colour. They all have to be either blue, that's all blue or all red. They can't be all green because there's only 3 green. And they can't be all yellow because there's only 2 yellows. So that's 5 choose 4 plus 6 choose 4 all over the total. Right, does anyone need me to do any part of number 3? Can I do part 3? No problem. You can. If I put this over this side, it might be better. Jesus, what am I doing? Right, okay, which part did you say, Kira, sorry? 3. Right, the four discs are different in colour. So that means you want one blue, and one green, and one red, and one yellow. You have it? So it's like blue, 5 choose 1, multiplied by 3 choose 1, multiplied by 6 choose 1, multiplied by 2 choose 1, all over whatever the total was at the start. You added them instead of multiplying them. Right, okay. Anyone need me to does anyone need me to finish that or anything, or do any part? You want me to finish it? Right, okay, so there's 5 blue and you want to choose one of them. Right, n means you multiply. There's 3 green and you want to choose one of them. N means you multiply. There's 6 red and you want to choose one of them. N means you multiply. And there's yellow, there's 2 yellow and you want to choose one of them. So that's how many different ways you can pick them. So you work all that out, right? And go away. Do they multiply it out for me? Which part is this? Part 3. When you multiply all that out, you get 180. Okay, so then the probability that they're all different colours, you have 180 ways of doing that, and over the total number of ways, which you worked out earlier on, didn't you? Which is 1820. Is that alright? Is that okay, Eva? Right, are we all alright? Right, okay, and does that cancel down? Probably does, but who cares? 55 over 182. No, I looked at the wrong one. 9 over 91. Is that okay? Right, any other one that you need me to do? No, right, I'm going to give you more of them to do in a few minutes. Right, okay, for the moment though, we're just going to read through these probability simulations. Right, okay, so this is like, say you want to, you have 6 girls, and you want to choose, can I just read the example? Right, example 1, right, okay, with every household, with every breakfast cereal pack, there are a free coloured toy. There are 6 different coloured toys. How many packs of breakfast cereal do you need to buy to collect the 6 different coloured toys? So, different cereal, there's a different toy, right? Okay, so you're not going to go out and buy 100 packs of cereal, right? Okay, so what you do is you get a dice. And you say number 1 is the Cocoa Pops, number 2 is the cornflakes, number 3 is the Weetabix or whatever it is, right? Okay, and then you keep rolling the dice until you get each number has come up at least once, right? Is that okay? That's a simulation, right? So rather than going out buying loads of cereals, right, you do a dice because there were 6 of them. Is that, yeah, I told you it was a bit dumb, okay, right? Okay, you could also pick random numbers, get your calculator, give each cereal a number, 1 to 6, and then you can use your calculator to generate random numbers between 1 and 6 and see how long it takes you for each number to come up. Right? Is that okay? Simulation. Right? Okay, use a spreadsheet, use a spinner. Get your friends to buy some boxes to see how many you need to buy to get a full set. Right? Yeah, are we all okay with that? The advantages of simulations are it is quick and inexpensive. You don't have to go out and buy all those cereals. It's quick. You only need 1 dice, right? When using a spreadsheet, you can get several hundred pieces of data. Okay, so if you use a spreadsheet, right, it'll automatically generate hundreds of examples for you. And you can adjust the probability to cater for events that are not equally likely. Right, yeah, okay, right, is that alright? Look at this one, there's example 2, right, in families that have 5 children, we wish to investigate the probability that boys outnumber girls. What are you going to do if you want boys and girls? You're not going to go and make loads of women have babies. What are you going to do? You just have 2 answers, so give me a simulation you would do. What would you do? Throw a dice? Toss a coin? Toss a coin, wouldn't you? Heads are boys, tails are girls. Right, okay, is that right? A simulation, right, is just doing an experiment you're able to do as opposed to a one that's impractical to do, because the other one is send a load of women out to have babies and wait 9 months to see what they have, right? Families of 5 children wish to investigate the probability that boys outnumber girls. Devise a simulation of this situation and use it to determine whether the probability is more or less than or equal to a half. Right, assume that there is an equal chance of being a boy or a girl. Suppose you choose to toss 5 coins at a time to stimulate the genders of the 5 children in the family. So there's 5 children in the family, so you do 5 coins at a time. So we got tails is obviously a girl, so you got 5 tails, so that's 5 girls. Then the next time you did it, you got 1 girl and 4 boys. Next time you did it, you got 2 girls and 3 boys. The next time you did it 5 times, you got 3 girls and 2 boys, and so on. Right, okay, however many tosses, after 100 tosses, right, okay, we get the following results. So boys 53, girls 47. It appears the outcomes are fairly even and that the probability that boys outnumber girls is about a half. Right, that sentence doesn't make sense. The probability that boys is a half and girls is a half. Using a spreadsheet, this experiment was simulated and the result was shown below, so it's 48.52, so it's about a half. Right, okay, are we all alright? Simulations, right, so instead of sending people out to have babies, you toss a coin. Instead of going out buying 6 different cereals, you throw a dice. Okay, yeah, someone had something?
What would they ask you in the exam?
I couldn't possibly tell you because I've never seen anything like this. That's why I was saying read this yourselves, right? This example could also be modelled rolling a dice. So if you get numbers 1 to 3 indicates a boy and 4 to 6 is a girl, if you didn't have a coin. Random numbers using a calculator or a table of random numbers. 0 to 4 indicates a boy, 5 to 9 indicates a girl. So random numbers between 1 and 9. Why you don't do random numbers between 1 and 2, I don't know. Right, selecting a deck from a deck of playing cards, red indicates a girl, black indicates a boy. That's a good one. Right, okay, isn't it? So just keep picking cards. right? But keep putting them back so that the probability, because the probability doesn't change, or it doesn't. It's always a half, right? Will we look at this one? 4 people are selected at random from a large crowd. What is the probability that 2 or more of these have birthdays in the same month? Right, okay. So devise a simulation that could determine the probability of this happening. Right, possible simulations. Write down the 12 months of the year on separate cards and draw them out of a box. Okay? Remove all the kings from a deck of cards, so then from each one you're down to 12 cards per suit, aren't you? Right? So for the 12 months, so the ace would be January, 2 would be February, 3 would be March, and so on. And then randomly select cards. Right, okay. Use a calculator or a spreadsheet to generate random numbers from 1 to 12. Right? Toss a dice and a coin together. There are 12 possible outcomes. So you need your two-way table, a head with a 1, a head with a 2, a head with a 3, a head with a 4, etc. Right, and then you assign each one. A head with a 1 is January, a head with a 2 is February, a head with a 3 is, and so on. Right, there's the simulation. Right, okay, and then simulation result, shared birthday, no, whatever, right, simulation result 1 is, so these are the 4 people, month 6, month 8, month 1, month 2, there was none of them had the same birthday. This is the second time you did it, month 1, month 8, month 1, month 11, 2 people were born in January, is that okay? Here, month 5 months, so there's no one the same, etc. So they're different simulations, they give you examples. The above 6 results were found using the random number function on a calculator. When this experiment was conducted 100 times, the following results were recorded. Shared birthday, yes or no. From these results, we can conclude that the probability of 2, 3 or more people from a random group of 4 sharing the same birthday is about 45%, because 45% of them shared, 55% of them didn't. Is that okay? Right, it really is a load of jargon, okay? Right, this answer seems surprisingly high, but the true calculated probability is 42.7. Right, okay. Right, sorry? No, I've never seen them on. Right, okay, but they're on the syllabus, so we have to cover them. Let's look at some of the exercises. So question 1 here. One of 20 different vouchers are given away in a packet of crisps. You need a full set of vouchers to get a model car. Carry out a simulation to estimate the number of packets of crisps you would need to buy to get a car. So you need to get all the numbers from 1 to 20. So what would you do? Calculator, generate random numbers between 1 and 20 and see how long it takes you to get all the numbers, so each number once. So you get number 1, number 2, number 3, and so on. Is that right? Okay. Carry out a simulation. You're not going to carry out a simulation, and no one will ask you to carry out a simulation inside an exam. Right. So a menu has 3 options: meat, fish, vegetarian. 2/8 of diners choose fish, 1/4 blah blah blah. Explain how you would simulate the choices of the next 10 customers. So you need something with 3 options. So what are you going to do? Say that again? 3 cards, yeah. A dice, and maybe 1 and 2 is meat, and 3 and 4 are fish, and 5 and 6 are vegetarian. Yeah, good. Or you could make a spinner with 3 different sections on it, and so on. Right, the list goes on. Right, you can see how stupid these questions are. Right, carry out a simulated experiment to determine the probability to correct to 2 decimal places that in a family with 4 children, the girls outnumber the boys. So we're doing girls and boys. The obvious choice there is what? Toss a coin. Yeah. So you 4 children, so that means you'll be tossing it 4 times and writing down your results. And then you toss it another 4 times and write down your results. Okay, and you should probably do it about 100 times. So that's 400 times to toss the dice. At a road junction, it is known that 80% of the cards turn left and 20% turn right. So right and left. So what are you going to do? Coin. 2 choices. Coin. Right? Okay. Number 5. The ring dogs have a 0.7 chance of winning their home games and a 0.4 chance of winning their away games. If they play 12 home games and 13 away games, how many games should they win? Make a simulation of this situation and find out how many of the 25 games they should win. Oh, don't mind that. Yeah, you get the idea of it, don't you? Yeah, I'm sick reading those. It's pretty dismal, really. Okay, right. So for the rest of the class, will we go back? I'm going to give you some more of the independent events ones because you hadn't got on to the harder type ones, and I'm going to give you some of the permutations and simulations ones. Okay. So between now and tomorrow, will you go back and do page 215? I'll put it up in Teams now in a minute. Page 215, let's do 12 to 16. Okay? And then on the permutations and combinations page, let's do page 218. You've done up to 3, so let's do 4 up to 9. Okay? Right. So between now and tomorrow, those. Sorry, that was stupid of me. And I'll put up both those pages on Teams now. And I'll stop recording.